local maximum or minimum. So there's a word for this, extremum. Extremum, plural with extrema. So let's call it extremum because otherwise I have to say always a maximum, minimum, and so much. So as local extremum at some point x0, y0, and its partial derivatives at this point exist. Then they have to be equal to 0. They have to equal 0. So this is the first test. In other words, if it is local minimum or maximum, and the partial derivatives exist, then they both have to vanish. The converse, however, is not true. If both partial derivatives vanish, it does not mean that it is a local maximum minimum. You have a question? Yeah, I knew that. It's always the case. I try to save some space, but then I have to go over it again, so I lose more time, right? More space. So I mean the two partial derivatives. This fx. Let's just do it anyway. Is that better? Okay. So converse is not true. It could be, which we discussed even in the one-dimensional case. Think of the y equals x cubed. Function x cubed has vanishing derivative, but the graph looks like this. So point 0 is not the point of maximum or minimum. But there is a test which involves second derivatives. So there is a second derivative test. Namely, we form the following quantity. We take the x0, y0 times fyy at x0, y0 minus fxy. This assuming, of course, that all of this exists. All of these derivatives exist and are continuous at this point. So the test is the following: that if d is greater than 0 and fx at x0, y0 is greater than 0, then it's a minimum. Then okay, I'm abbreviating. That x0, y0 is a minimum. If d is greater than 0 and fx, let's say less than 0, then maximum. I mean, x0, y0 is local minimum, local maximum. And if d is less than 0, then it's what's called a saddle point. It's a saddle point, like a saddle point. So neither maximum nor minimum. And the saddle is what you get when you look at what is called hyperbolic paraboloid. Yes? Yes, it is. That's right. So remember, we had there's this figure, one of kind of the fanciest quadratic surface that we discussed, the hyperbolic paraboloid, which looks like a saddle. So if you go in some direction, you fall down. But if you go in other directions, you go up. So it's neither maximum nor minimum locally. Okay. So that's if d is less than 0, then that's the kind of point you have. So that's how you know it's not. But otherwise, if d is 0, no information if d is 0. If d is 0, it will go either way. Okay. We didn't talk much about why this criterion is true. I only made a few comments. The point is that to understand it, you should really look at just quadratic surfaces, because as we discussed, a function, the first approximation to a function is a linear function. In other words, you approximate by the first derivatives, and the next level approximation is given by quadratic derivatives. So, but two functions have the same quadratic derivatives if they have the same sort of Taylor expansion in degrees 1 and 2. And the higher order terms in the expansion, they don't really matter locally, when you look at it locally. So to understand what's going on here, you should look no further than just quadratic functions which are polynomials of degree 2, combined degree 2 in x and y. And for such functions, this expression is actually a number. And if you just plug this formula, in this formula some of your favorite examples, like elliptic paraboloid and hyperboloids and this kind of functions, you will see how this criteria work. The reason why we choose this fancy combination of second derivatives is that the point is that the behavior of the graph is not necessarily determined by the coefficients of the polynomial, but they're determined by sort of the main axis. When we talked about quadratic functions and quadratic surfaces, we talked about the fact that you can always make a change of variables to bring it to a nice form. Well, when you bring it to a nice form, you will get a very simple expression for the second derivatives, and then this will become simple form, meaning say ax squared plus by squared. If you bring it to such a form, you will see that this is a and this is b and this is 0 because there's no cross term, right? So for such a function, if f is this function, d is equal to, let's just kind of small insert here, d is equal to ab, and so then you can very easily see what those scenarios correspond to, because d greater than 0 and fx greater than 0 means that a is positive and d is positive. So we are dealing with a paraboloid. The graph of this function is a paraboloid. It's an elliptic paraboloid, which goes like this. So clearly we have a minimum. This case corresponds to both a and b being negative. So that's upside down paraboloid, maximum. And when it's less than 0, it means that one of them is positive and one of them is negative, and that gives you the hyperbolic paraboloid. So this is a way to understand this criterion by simply looking at such expression, at such functions. And then a more general quadratic function can be always brought to this form, and what tells you what the d is for that form is this expression. Anyway, we don't need to get too much into detail of this criterion. You just have to know this criterion. And you should understand it for this particular function, how it works, ax squared plus by squared. Okay, so that takes care of the local maximum and minimum. And in some sense, it's a little bit disappointing because we don't have a conclusive criterion. But the same is true also for functions in one variable. Functions in one variable, we don't really have, if you just use first and second derivatives, you cannot really make a conclusive statement in general whether it has a local maximum or minimum. So it's not so surprising. So what's more kind of pleasant in some sense and satisfying is the case of global maximum and minimum. In this case, we can usually find a complete solution by following a basic algorithm. So let's talk about this, global. So global maximum and minimum is a totally different game, where you're actually given a certain region. Say if it's a function in two variables, you're given a region in R2, or if it's a function in three variables, it will be a region in R3. And you have to find points within that region only. You don't care about what happens outside, only within that region where the function takes the maximum and minimum values, right? So the algorithm here consists of essentially 2 steps, although you can sometimes phrase it as in terms of 2 steps, sometimes in terms of 3 steps. But basically, the first step would be to find global extrema. First of all, you have to find points in D where both partial derivatives vanish. These are the points which are suspicious because of the first derivative criterion, because those could be the points of local maxima and minima, and local maxima and minima could potentially be global maxima and minima as well. Right? So we have to find all of those points. In fact, you don't have to look at in this part of the algorithm. You don't have to look at the boundary, because the second part of the algorithm takes care of specifically of the boundary. But when you write these formulas, okay, if you get a point on the boundary, you include it as well. Why not? And the second part is to focus exclusively on the boundary. Focus on the boundary, and find extrema on the boundary, on this boundary. Find the extrema of the function restricted to this boundary. So here there are basically essentially two different ways, two different approaches. If the boundary is linear, in other words, if it is given by linear equation like x equals something x equals 5 or x plus y equals 0, you can simply substitute this equation into the function and get a function in one variable, and then solve the problem by doing functions in one variable. Right? So first possibility is boundary is given by linear equations. Given by linear equations. Linear meaning is just degree 1 in x and y. Example. Let's say f is equal to x squared plus y squared, and the boundary, one component or segment of the boundary is, say, x plus y equals 0. Well, then you can simply express y in terms of x, y equals negative x, and you can substitute it into the formula. So instead of a function in 2 variable, which you originally have, you will see that when this function is restricted to the boundary, it effectively becomes a function in 1 variable, namely x. So you get that this restriction to this x plus y equals 0 is just, x squared plus negative x squared, which is 2x squared. So you get a function in 2 variables, but on the boundary it becomes effectively a function in 1 variable. If you have a very complicated equation for the boundary, you may not be able to easily express y in terms of x or x in terms of y and then substitute. But if it's a linear equation, you can always express easily one in terms of the other, and then you simply substitute, and then the remaining variable will be the only variable left. You will get a function in 1 variable. So then just solve the problem by using the methods of the calculus of 1 variable, which is you just look at where the derivative of the function vanishes on that. Well, in general, it's not going to be this entire line. It's going to be some interval on this line. Like I said, it's only a component of the boundary. In general, the boundary is going to have many components. For example, the boundary could have this as a component, and then it could have part of the circle as another component. So, except, of course, I didn't draw the right. This is not x plus y equals 0, but it's x equals y. Okay, let's do it the right way. This is x plus y equals 0. Okay, so maybe this is not, it's not good because I don't want to write it like it's, my function is x squared plus y squared, and let's just make it something complicated. It could be something like this, right? I'm not saying I'll put exactly this one on the exam. But I'm just saying for the sake of the argument, okay, just as an example. So you could have this very simple component like this. When you restrict your function, it becomes a function in 1 variable. You can choose which one, x or y. You express the other one in terms of this, the original one, so y in terms of x. Substitute, get a function in 1 variable. Solve the problem, namely find the extreme of the function on this interval by using methods of 1 variable calculus, 1 variable. That's the first possibility. The second possibility, you have something like this, which is given by a much more complicated function. Rather than x plus y, it could be something with higher degrees, or even could be some more complicated functions altogether. In this case, this method will not work because you will not be able to easily express 1 variable in terms of the other and substitute. So you have to use something else. And that something else is Lagrange method. So I would say this is what I call 2a. So that's the method, that's the easy method. And the slightly more complicated method is Lagrange method. Lagrange method. So Lagrange method is about, so in this case, it's about solving a system of equations. So in this case, your component of the boundary would be given by the equation g of xy equals k, or g some function. And so you will write the following equations. You will write nabla f. F is a function which you try to maximize, minimize. Is lambda nabla g, and then you also have g of xy equals k. So solve this system. And then, of course, there is an additional issue, which is that there could be corners. There could be points which are not smooth on the boundary. And these have to be treated separately. I mean, you can think of treating them not separately, but you can think of treating them within the context of 2a or 2b, because when you do that, you have to take care of the endpoints anyway. Or you can just think of corners as a separate entity, a completely separate entity, and just put them on the list at the very end. But you have to include them. Okay? So usually the way I explained it is you do the corners, which are corner by corners. I mean points which are not smooth points, like this. In this case, this too. So basically, it boils down to the following. You might have sort of an easy case where the boundary is smooth. For example, boundary could be an ellipse. This is exactly the example which we studied originally in class. In this case, there are no corners. There are no corners, so you don't have to worry about it. You just do Lagrange method here. Okay? But if you have something like this, then you have corners, and you have to take care of them separately. Or you can think of taking care of them as part of analyzing the segments of the boundary. Is that clear? Yes? Will Lagrange find them for us? That's a very good question. Lagrange will not necessarily find them for us, right? For exactly the same reason why the endpoints would not necessarily be found just from in 1 variable calculus, from finding points with derivative 0. What was the issue if you had a function in 1 variable? Let's say you have a graph of a function let me do it in this way. You see, here is a very good illustration because here this is a maximum point, which is also a local maximum. So it will catch it in at the first step if we were doing it for one variable function, right? But this is a minimum, and it's a minimum not because the derivative vanishes. The derivative is non-zero, but because it's the endpoint, because we can't go any further. Likewise here, remember we had a discussion about how there were 2 points, which were the points where the level curve of the function f were tangent level curves of the function f, which in my example back then was a linear function, were tangent to the level curve, to the constraint, to this curve, right? Now, okay, great, but what if my curve ended here? What if my curve was just like this, from here to here? Then okay, I would catch this one as a minimum, just like here. So it would actually be given to me by Lagrange. But what about maximum? Lagrange would give me this, which is actually not part of this segment, because my picture could be like this. My domain could be like this. And what would happen in this case is that actually the maximum would be achieved at the corner. So just because it's Lagrange method, it doesn't mean it doesn't have its own limitations, right? It has the same limitations as other methods that we have studied which involve derivatives. Right? It's a very good question. It's a very good point. Yes? That's a good question. So the question is, do we have to worry about saddle points when we're doing global maximum minimum? And the answer is no, precisely because it's sort of a different sort of game that we are. We will certainly catch them in part 1. Because in part 1 we are just grabbing all the points we can get where the derivative is at 0. So in particular we'll get a lot of saddle points in general. But I guess I didn't finish the algorithm. The point is that of course at the end of the day we're going to just evaluate our function at all these points. So the saddle points we'll just get rid of them in a natural way because they will just turn out to be fake. So they will not be maximum minimum. Right? So maybe I should say that the end of the algorithm is to evaluate function f at all of these points and find maximum minimum. Possibly multiple. It could be that there are 2 different points where you get the same value, so you have to list them all. So if the question on the test is give all the maximum minimum of this function on this domain, and let's say this function has 2 maxima, 2 points where it takes the same maximum value, and you only give 1, then obviously you will lose some points on this, because this would not be a complete answer. Complete answer would have to include all of the points with maximum value as well as points with minimum value. Now there are a couple of tricky points here as far as Lagrange method is concerned, which I wanted to emphasize. Well, first of all, I want to stress that Lagrange method is used in 2 entirely different types of problems. The first problem is the problem like I just described, where you have a 2-dimensional domain and you want to find global maximum minima. And then you have to worry about the interior of this domain, and then you worry about the boundary. And when you get to the boundary, if the boundary is complicated, you have to use Lagrange method, right? But there's a different type of problem altogether, where you just are asked to find maximum minima on a level curve. In other words, you don't have the interior, you don't have the 2-dimensional region with the boundary, but you just have a curve, right? So in that case, of course, you don't need to do part 1. You just do Lagrange method for this curve, and that's it. See, so that's an important thing to remember. That you have to understand what the problem is. If you're asked to just analyze the curve, you don't have to see what happens in the interior. Now, in all of this discussion, I assumed, so maybe I'll write it, Lagrange method can also be used to find maxima and minima on a curve like this, g of xy equals k. So in this case, no, there's no interior. No interior. So you don't have to do the partial derivatives on interior and so on. Just apply Lagrange method to this. And there are actually a couple of tricky points which we did not talk about in class, but which were part of some of the homework exercises, which I wanted to draw your attention to. So the tricky points are, there are 2 tricky points. Yeah. Where the Lagrange method doesn't work in the best possible way, as explained here. Okay. And the tricky points are, first of all, this works. Maybe I will just say it in one sentence. This works well. The method works well if, first of all, this curve is bounded. If the curve does not go to infinity. This is actually something we did talk about in class. I did give an example like this. If, number 1, the curve is bounded. You see what I mean? Bounded means that it is like this, as opposed to something which goes to infinity. More precisely, bounded means that you can cover it by a sufficiently large disk of sufficiently large radius. On the homework, there was an extra kind of tricky exercise, which was x cubed. I think it was something like x cubed plus y cubed equals 1 or something. And it looks deceptively simple because it looks almost like x squared plus y squared equals 1. So this is bounded, right? This is bounded because it's a circle of radius 1. But this is not bounded, so this is an important point. And the reason is, of course, that here you have sum of squares, and squares are always positive or 0. So if the sum of squares is equal to 1, you can see. All right. This is the sum of 2 numbers which are positive and equals to 1. So it means that each of them has to be less than 1, between 0 and 1. And that puts the bounds. Of course, x and y can only be between 1 and -1, right?